Kyoto. So, and first let's show the movie, and you can get it on the web for yourself. And I bet with probability 0.99 that they have this device in the chemistry or physics department here at KAIST, someplace. So the question is, it's a piece of glass with a windmill like a fan inside, and it's called a radiometer, and so there's very little gas inside, a rarefied gas. And then you watch the movie, and the question is, why does it spin? So we can put on the movie. Let's see. So this is from the web. Let's see if we can make it go. Let's see, this talking. Can we get it to go? Nothing? It's not spinning, so let's see. Not playing yet. There it goes. Okay, so it shines a light on the device, and it starts to spin. And only spins one direction. Okay, it's you can't make it spin the other way, I think. So,
what is the light?
Well, obviously the light makes a difference. So, and the question is, why does it spin? It's interesting that the Wikipedia article says, not so obvious. You can read the article on Wikipedia, and well, let's think about it. You could say that you put some pressure in the gas, okay, just like I put pressure on you, put pressure here, and it would force it to move. Now in a gas, the pressure is proportional to the temperature. Okay, so you could say, okay, so you made the, change the pressure. But that doesn't make sense, because it's a pressure gradient. The only reason you move if I push you is that the pressure on one side is different than the pressure on the other. Okay, but in the gas, the pressure is the same every place. Okay, so I heat it up, temperature goes up, pressure goes up, but the density is the same every place. So pressure is density times temperature, temperature goes up, but the pressure is the same every place. So it's like your friend is pushing on you from the left, and your other friend is pushing on you from the right, exactly the same amount, you don't move. So no pressure gradient. Okay, if there's no pressure gradient, then there's no force. If there's no force, Newton tells us F equals ma, no acceleration. But if there's no acceleration, we know the equation F equals ma. If F equals 0, says second derivative equals 0, first derivative is a constant. If you're initially at rest, the constant is 0, no motion. So, why does it move? So this is a homemade one. So it's a rather question. So one way to think about it, and Wikipedia gives two answers if you read the story on the radio.
Just a moment.
Yeah.
So the light comes from one side, one direction.
Yeah.
Then it gives us some there's a heat in the some force in the left side. In the
that's exactly, yeah.
Then temperature goes up in the left side.
And the temperature on the left side is not on the wind. Now you have the right answer. Okay, so we've got a very good student. We should give him okay. So you notice they have the windmills, so there are two faces. And the two faces are not the same. So one side gets hotter and the other side is colder. So that's the one explanation. Okay, is that if the temperature is not the same, then we're setting up a temperature gradient across the interface, and maybe that's the cause. So we look at solving the equations of fluid mechanics. with a constant temperature gradient. So that motivates the PD problem. If you set up a constant temperature gradient, that's a boundary condition for the PDEs. We'll just do the 1D case. Solve the, well, it's 2 space dimensions, but no time. So just look for steady state solutions. The faces are not the same. So there are 2 explanations given in Wikipedia. It's interesting. One gives this fluid mechanics explanation. The other one says, no, Einstein said it was the photons hitting the, so this Einstein and fluids. And Wikipedia article says, could be not clear. Okay. So Wikipedia says maybe Einstein, maybe fluid mechanics, maybe both. Okay. So in either case, it's a subtle problem. So let's write down the PDEs and solve the PDEs. Okay, so now we'll erase this, so let's write down the PDEs. No, we need lights. So let's write, I have no other view graphs because I'm still working on the problem. Now I try to draft the Young-Jum into the problem. And it's interesting, it's a problem in PDs, but no PD people have ever worked on it, and it's so simple. So it seems rather interesting. The only analysis that I know is by typing Liu and Shishun Yu in Singapore. And they don't use PDs. They use Boltzmann. So let's write down the PDs. So we have conservation laws. Let's see if I can remember them. So we have conservation laws of gas dynamics. Okay. The good thing about this problem is you don't need to know anything to get started. It requires no basic knowledge. But I'll tell you the equations of gas dynamics if you forgot. So we have conservation of mass. Oh, so let's write down the picture. So let's set the boundary value problem over here. So there are 2 boundary value problems we can solve. There's a few in the So here's the boundary value problems. So let's write down. So rho will be the density of the gas. U will be the velocity in the x direction. V will be the velocity of the gas in the y direction. Theta will be the temperature. Okay, E is the internal energy. Well, you heat up the gas, you get energy, but that's proportional to the temperature. So E is the internal energy. But that's just equal to, when I said all the units, just take it to be 3/2 times the temperature. That's usual. This constant of gas constant, capital R in the books, they'll just set that equal to 1. Well, that's not an issue. So that I have everything under pressure. P is the pressure in the gas, and I said P, I just take it to be density times temperature. Of course, there should be a gas and R there, but again, I said R equal to 1 because it's not relevant. Okay, and we'll solve, I can't solve the radiometer problem. The geometry is too complicated. You'd need, but this is the one that the engineers work on. And so we'll make this the x direction, this the y direction. and this the y direction, this the x direction. Okay, so the gas is inside. Yellow. So in this one, the gas is between two parallel plates, and in this one, the gas is in the upper half plane. And I'll set, as I said, we'll put a temperature gradient on the wall, just as we, on the video from the web. This is clearly setting up, there's a temperature difference as you go from one phase to the other. So the easiest one we can imagine is that the temperature is just a multiple of x. So as you move along, the first derivative of the temperature is a constant. Now, I've noticed, and now here we have two walls, then we make the other one, to keep it simple, exactly the same. You could make it more complicated if you made them different, but okay. And we'll make the difference here, the H, which is thin. So it's a narrow slit with a narrow channel. I should remark that one application, not that I have any interest in making it money, but
Sector 2x maybe, the upper boundary value.
theta, it's just a number. Theta sub 1 is a constant.
Upper. Same?
Yeah?
Yeah.
Now,
Same boundary.
the boundary is x is this way. So theta is a multiple of x on y equals h over 2, and y equals minus h over 2. So it's a function of x on the boundary. So it's not constant.
So the same boundary.
Same boundary condition. Same boundary condition. Exactly the same. Now you might say that I thought about it. Okay. Well, that means as x gets negative, the temperature is getting negative, which is impossible, of course. So we'll only be interested in the piece of this where x is positive, or another way to think of it is, if you make the change of variables x equals, say, x1 plus constant a, then the boundary condition theta 1x becomes theta 1 x1 plus theta 1 a, so it's no restriction, and then you just change variables. The equations don't care whether you shift the x or not, so the equations are invariant under translation. And now it's affine. It's a constant plus a multiple of x1, and again, as long as this x1 isn't too big, or this one is positive and this one is positive, then the temperature will always be positive. So I'll never worry about x being negative. So I'll only work in this picture always to the right. Again, in this picture always to the right. Okay, so that's theta equals the boundary conditions. So that's the boundary value problem, but I didn't write down the partial differential equations. So now one other point is, what boundary conditions to put on the velocity? Well, clearly, the velocity in the y direction, the gas can't go through the boundary. So here, we have to have v equals 0, and v equals 0, and over here we have to have v equals 0. So the gas can't go through the boundary. Now, how about u on the boundary? Now this is an interesting point. If we make viscous boundary, make a viscous fluid, then the usual theory of viscous equations says we'd have to make the u equals 0 on the boundary, but the velocity, the particles stick, the fluid sticks to the boundary and can't flow. This was an interesting problem. Okay, so we'll look at that in a second. Okay, what happens if you put u equals 0? Should u be equal to 0, or maybe not? This is become a fundamental issue, and Maxwell himself when thinking about this problem. So Maxwell knew the radiometer. It was in the 19th century, and was thinking about this. And this caused Maxwell to change the whole nature of boundary conditions for PDE, which usually, again, PDE people don't worry about. They say, mostly PDE people say worry about the equations and not the boundary conditions. There's a subtle point here. So let's write down the balance of mass. Okay, so now you know all the letters. So balance of mass is just this. So conservation of mass. Okay, then we have conservation of momentum, which there are two, because there's momentum in the x direction and momentum in the y direction. So conservation of momentum looks like this. Now here there's a stress tensor, which I'll write down, but we'll do it in the easy case. So this one I have to tell you what it is. So it'll be, this is T11, there'll be T11, T12, T12, T22.
Rho u squared?
This is rho u squared. Sorry. And then plus d dy rho uv minus T12. And so I have to tell you what the capital T's are, which is the stress tensor. That's the thing that causes forces in the body. And then we have the conservation of energy, which is a little more complicated. So there's two kinds of energy. It's capital E. Well, there's the energy due to the heating of the body. That would be just the density times the temperature, because E or a multiple of the temperature. Okay, so that's the potential energy you could think of, and then the kinetic energy, which is rho over 2 u squared plus p squared. So if you want to think of this as potential energy or thermal energy, and this is kinetic energy, and the total energy is the sum of the two. So the energy equation will be d dt. Okay, E, okay, plus d dx. Now this guy, okay, times u plus d dy. This guy times v. Okay. And then some other terms, so let me get those straight. And then it's the stress tensor enters, so I don't make a mistake. And it's d dx u t1 plus v t12 plus d dy u t12 plus v tt2. That's the left-hand side. You can either put the, oh, this is on the left-hand side, sorry. Equals, I have it, equals, this one equals, that's the right-hand side, and then the rest of the right-hand side is the heat flux. Okay, so that's the conservation laws of mass, momentum, and energy. So there are 1, 2, 3, 4 equations and 4 unknowns. Rho, U, V, theta. 4 equations and 4 unknowns. Now, I have to tell you what the T's and the Q's are. The Q is easy because that's the one that gives you the heat equation. So the Q is a vector. And we know from Fourier that Q is proportional, some constant proportional to the gradient of the temperature. So it's the partial of theta with respect to x, partial of theta with respect to y. So we know Q. So if this constant may or may not be a constant. So K is in general it's a function of theta. But if it was a constant, then this is just the Laplacian, as we would get from the right-hand side of the heat equation. Okay, now I have to tell you what T is. Okay, and okay, so in an ideal gas, okay, we have the temperature, stress. That's why I used theta for the temperature, by the way. Okay, why do PD people always use theta for the temperature? Because they need T for the stress. So you can't use, and then sometimes we need T for the blow-up time, if we're proving blow-up time. So you can't T one letter, you can't use it for three different things. So I always use the theta for the temperature and T for the stress, and blow-up time, well, I need another letter. Okay, so what's T? Okay, so the simplest choice is T equals minus P times the identity. Okay, that would be the ideal gas. Okay, but if we want to be a little bit more general, we might put in a viscous term. So T is in our case, is a 2x2 matrix, if you want to think about it. So I'll put double lines to remind you. T has 4 components, but T12 is T21, so it's symmetric. So this one is just P, and the I goes, the P hits the upper left and bottom right. So now we need to know, we might have viscosity. So what's the law of viscosity? So we have, so now you can imagine that I'm writing down the Navier-Stokes Fourier theory. Okay. Which in abbreviation is NSF, which in this case does not stand for National Science Foundation. Okay, so this is the Navier-Stokes Fourier theory. Okay, there's a big literature on the Navier-Stokes Fourier, sometimes called compressible Navier-Stokes. So this is sometimes called compressible Navier-Stokes. Okay, and I think there's even a book on it by Pierre-Louis Lyons. So, there's a book. And there's a lot of papers written by the Czech group in Prague. I have to remember his name. I'll remember. Okay, they write lots of papers. Okay, and I'll mention some connection, the PDE issue here, because this we can learn a lot about PDEs from this, to me, from this problem. Okay, so what's the viscous term? So I have, can I move this over so you can see? Yeah. I'll move it back. Let's do that so I don't forget the viscous term. So TV for Navier-Stokes is lambda trace D delta ij plus 2 mu dij. Okay, so dij, let's write it down. So dij, d11, so dij is the partial of u1 with respect to x, ui with respect to xj plus uj. So if I had given the mixing notation, so that's dij. Now let's think of it. So in this notation, U1 would be U, and U2 would have been V. So let's write it down. So D11 on our example is 1/2 the partial of partial v with respect to x, partial v with respect to x is 2 with partial v with respect to x. So it's 2 lambda partial u with respect to x plus 2 mu d11. Well, d11 is again partial v with respect to x, partial mu with respect to x, right? So it's partial 2. I have that right. And I hope I have it right. And I have to make sure of my constants. Make sure I have the Navier-Stokes rule correct. 2 mu, that's right. Dij is 1/2. So
you're writing T11.
this is T11.
T11.
Yeah, so this is T11. Okay, so we have a bunch of constants. So this is, the 2's cancel. So it's lambda plus 2 mu, partial u with respect to x. Okay, well, the same story. That's T11. T22 is exactly the same way, and u is replaced by v, and x is replaced by y. And last but not least, T12 is, this one goes out, so it's just 2 mu, and it hits this 2, so it's just mu partial of u with respect to y plus v with respect to x. So I know all the viscous terms. Now, lambda and mu have a relationship, which is, I have to remember, lambda is minus 2/3 mu. So the usual one that people use is lambda equals minus 2/3 mu, where mu is positive. So this comes from Boltzmann equation, kinetic theory of gas. It's not important for us, so let's substitute that. So I want everybody in terms of mu. So lambda plus 2 mu, lambda plus 2 mu is 4/3 mu now. So this gets replaced by 4/3 mu. Okay. Okay, so now we're ready to solve our boundary value problem. Okay. First of all, we only look for steady state solution, because after when we shine the light on the radiometer, it started to spin, and it reached steady state very quickly. So let's use the blue, or yellow is easier to see. So I'll cross out all time derivatives. We'll need this in a second. Yeah? Okay. So first let's cross out all time derivatives. Let's look for steady state solution. Okay. Now we need something. If it's viscous, I said, oh, let's put, if we're going to do viscous fluid, let's put u equals 0 on the boundary. Okay. Now, here's the good news and the bad news. Okay. It's the same news. Most everybody in the room is a mathematician and not an engineer. So a mathematician, we say, oh, let's see if we can prove existence of solutions. Okay, so let's prove existence of solution. What function will satisfy the boundary condition u equals 0, v equals 0, theta equals theta 1 of x for this problem or this problem? That's not very hard. Well, I know which one that satisfies the boundary condition. One that works is u equals 0, v equals 0, theta equals theta 1 of x, every place. Okay? That certainly satisfies the boundary condition, but it's the same as the boundary condition. Okay, so now we have to see if it satisfies the PDEs. Well, let's look at the PDEs. We'll pull out the viscous one later. Okay, here U equals 0, 0. V equals 0, 0. U equals 0, 0. UV equals 0, 0. U equals 0, 0. V equals 0, 0. So we satisfied mass and momentum. How about energy? Steady state. U equals 0, 0. V equals 0, 0. U equals 0, 0. V equals 0, 0. U equals 0. V equals 0. We have to worry about the Q's. Okay, let's pick a simple case, okay, where K is a constant. If K is a constant, then the derivative of theta with respect to x is constant. If I plug in a constant here, I get 0. Derivative of a constant, 0. Useful fact. This one, it's independent of y. Derivative is 0. So we've satisfied the equations, except let's worry about, oh, but I forgot about the viscosity. So we're over here. Viscous term. What's the viscous term? Well, here it is. What's T11? T11 was partial v with respect to x. 0. U is 0. T12, partial part v is 0 is 0. V is 0 is 0. So it's solved. Oh, we write a paper. I've solved the Navier-Stokes Fourier problem for this model problem. Let me send it in and publish it. Okay, so you send it to Math Journal, and they say, okay, it's not a very deep result, but it's true. Then you send it to Engineering Journal, and they said, not a very deep result, and it's not even what happened in the laboratory. Don't go to Wikipedia. So something is wrong. That's why the title of the story here is Ghost Effect. So Sony in Kyoto calls this the ghost effect. Okay, the engineers call the problem thermal creep. Okay, so there's something wrong. So the Kyoto group and Taiping say, okay, that means the model is no good. Okay, you shouldn't use for rarefied gases. You should not even think about using Navier-Stokes Fourier. You should solve the Boltzmann equation, more fundamental model for rarefied gases. Okay, that's one possibility. Okay, but my goal was to say, oh, maybe we can study the PDEs a little more carefully and see what's wrong with the PDEs, and then write down a better system of PDEs. And Sony, in his survey article, also mentions that, though I write down my PDEs, which are sort of similar to Sony's. One thing we certainly learned, with no offense to the math people, is those people who insist upon proving theorems about compressor with Navier-Stokes should have to keep in mind that even when they get an existence theorem, even existence uniqueness, it can be completely stupid, vacuous, because okay, the math is perfect, but the engineering is completely wrong. When does it go wrong in all the theories of gas dynamics, okay, PDE people? They always have trouble when the density gets small, near they get to the vacuum. They have a lot of problem. Okay. Otherwise, no problems. Okay, so they have the density gets small, okay, but what is it telling us? The gas is becoming rarefied, just like in the radiometer. If the gas gets rarefied, no wonder they have problems. It's not just mathematical problems. They've reached the limit of the model. The model cannot be right because it doesn't even predict the experiment. Furthermore, what Maxwell realized, how did Maxwell go about setting up the problem? Maxwell realized that there was a problem, and Maxwell realized, among other things, that in such problems, even though you'd like to put viscosity, telling you that U equals 0, V equals 0 on the bottom, Maxwell realized that the U equals 0 condition didn't work. So something goes wrong. And that just means that as we set up the temperature, okay, the fluid starts to flow here. Okay. So the gas is moving, and it's moving that direction. On the other hand, if you set up U equals 0 there, it means there's going to be a jump discontinuity between the gas motion and the boundary condition you set up. So that's called the slip condition. So there's a slip boundary condition. So Maxwell introduced the slip boundary condition. Okay, so usually we don't think that it's going to be a jump discontinuity between the boundary and the thing. But what it really is a boundary layer, and everything's forcing ourselves down into a thin layer that in the limit we see this jump discontinuity. Okay, so that's the question, and then the question is what to do. So what did I do? I said Navier-Stokes Fourier theory, perfectly nice mathematics, that gives the wrong physical answer. So we have to do something. So the math people, so Taiping Lu and Sone and others, okay. So it's a combined Japanese-Taiwanese effort, have done some results, but as they always say, you have to use the Boltzmann equation. Which I won't write down, because we won't do that. So you have to use the Boltzmann equation. But the Boltzmann equation is messy, and it's nonlinear. So the Boltzmann equation, I talked about it last time I was here. So the Boltzmann equation is one, messy, because it's an integral differential equation, and nonlinear. So then, what do? Well, they can't avoid that it's messy, but they can avoid the nonlinear by linearizing. So then they linearize, and they solve the linearized Boltzmann equation. So they linearize about some constant state, and then try to solve this problem. Okay, so this, the most mathematical of the papers appeared in the Quran journals. Communications, Pure and Applied Math, 2007. Okay. So, good math paper, and they get nice estimates on for the linearized problem on exactly what the velocity is in this channel. Okay, they didn't do the half-plane problem, but they did the channel. They don't write down the answer. They just give estimates. Okay. So what you're saying, I say, okay, but I want to write down what's the answer. Okay. So no estimate, what's the answer? Well, then it's either solve the now linear Boltzmann equation explicitly. They can't do it. Okay? So then what do people do? So then Sone, Aoki, and others. Okay, they ran the computer. Okay, so the Japanese group, the engineers, they run the computer, and then they get nice answers. So they changed a nice PDE problem, in my opinion, into a big scientific computation problem, but they know how to do that, I don't. Okay? And they get answers. Okay. There's a third approach of Henning-Struckbrook, which is in the, among other places, it's the IMA Journal. That's not the one in Minneapolis. That's the IMA Institute for Mathematics Applications in England. They have a math journal. So it's a journal on applied mathematics. And he has a nice survey there. And he makes doesn't solve Boltzmann. He does his own approximation of Boltzmann, so-called relaxation approximation, which I like to use too. Okay, and then linearizes, and that one he can solve. So that's the only place I know where there's explicit solutions. And again, his pictures agree with Sonnet, but it's still linear. So in other words, so far as I can see, all the analysis is linear. So my goal in going into it is say, okay, can we change it into can we solve the nonlinear problem exactly? Closed form. Not an existence theorem, but a formula. So the goal was to find an exact formula for the U in here, because the gas actually does move to the right. So what's the formula? At least a formula. Okay, so how to do it? Well, I just told you that something's wrong with the equations. So we're missing something with the equations. So I add one more term. So it means that Navier-Stokes Fourier theory fails. So now, but as I said in the lectures last year, one way to think about Boltzmann is it can be, in some sense, in my opinion, approximated by Korteweg theory, a higher order term. So Boltzmann is some awful set of, well, it's one equation, but hard to solve. Whereas the Korteweg theory sort of captures all the ideas of Boltzmann. Okay, not unique to me. And Sonnet, in his survey, which is in the Annual Reviews of Fluid Mechanics, I forget the year, not too long ago. He writes down what he thinks are his equations. That is, it's his version of this term. But what he didn't try to do is solve it. Okay. And I feel rather remarkable that you can actually solve the equations. Closed form solution. Okay. So well, I'll raise here. So the question is how to do that and how to set up the problem. I don't want to erase anything, and I always have one more blackboard. Okay, so let's see which one I want to do next. Let's I'll do it the same way I did it here. Okay, so let's do I guess I'll do the scaling first. So let's do the scaling. So this is a problem that this one, from setting up the equations, is easier than this one. And the reason is because we assume that h compared to some typical length going this way, so pick a typical length, L. Okay. Why do we need a typical length going this? Clearly this one has height h. Why a typical length going this way? Because if L is very small, the typical length there, we're only looking at a small interval there, then h is much bigger, and that won't capture the phenomena of the gas going this way. So if this is 1 centimeter, we need this one to be 100 centimeters, something. Okay. Otherwise, we won't see what's interesting. So we have to make some typical length on the height and typical length on the going along the wall or walls. Same thing. Okay, so we have a typical height and typical length, which tells us that we should make a change of variables. So, whoops. So we set x equal to L. So and y equal to y bar h. So now, as x bar, the new variable, goes of, say, length 1, it's dimensionless, then the x goes of the length L. So it's the right amount of distance in the x direction. The same thing here, that's the L here. So I say y equal to a new variable, y bar times h. So as y bar, say, goes between minus a half and plus a half, the y will go between minus h over 2 and plus h over 2. So I made the problem dimensionless and captured the essence of the scale. And the assumption is that h over L, which I set equal to epsilon, is the small parameter. Okay, so let's see if we can do that without erasing anything. Okay, so the good thing about, can you see the blue? I haven't used blue yet, so let's do that. And the good thing about the blackboard is we can do the changes of variables. So if I set x equals to x bar L, that means this becomes bar and an L. And y equals y bar h this becomes I h. This one becomes L. This becomes h. This becomes L. This becomes h. And this one becomes L, H, L, H, L, H. So far, so good. Okay. Why do I do that right away? Because now let's multiply. Since it's time, I'm going to take the timed ones and erase them, so it gives me a little more room, because we don't worry about the time derivatives. We're looking for the steady state solution. Okay. Now multiply both sides by h. So this is the useful. So now we have h here. But h over L is epsilon. So let's erase that. And now we see the advantage of doing the channel problem first. Because the channel problem tells us that the leading order in epsilon, this term is negligible. So I'll use the yellow chalk to erase, put a line through this one. Because the leading order in epsilon, all I see is the partial of u with respect to y, of partial of y of rho v equals 0. So let's erase that. So let's do that. So let's think about that. So the partial of y of rho v equals 0. If the partial of a function with respect to y equals 0, it means rho v is a function of x. Let's set y equals to 0 on the half plane, or y equals to minus h over 2, depending on the problem. Doesn't make any difference. Okay. So set y equal to 0 on the wall. So on the wall, this one is 0 because the fluid can't go through the wall. So it says the f of x is 0. So it says rho v equals 0. Well, for density, we're not doing the vacuum. Otherwise, there's no fluid or no gas. So rho isn't equal to 0, which means v equals 0. And now we see the power of the channel flow problem. We can immediately, to leading order, if the channel is sufficiently thin, said v equals to 0. So instead of having to write down all the equations, we can take the chalk very quickly and reduce the number of equations. Oh, I didn't say something very important about P. Okay, when I said about the known motion, I forgot to say the important thing. Okay, we look for solutions where P is a constant. Oh, I left out, so forgot about it. Say 1. Okay. Otherwise, I said U equals 0, V equals 0, the trivial solution, that implied, okay, of course, if P wasn't a constant, then something might happen. But I'm looking for P equals constant solutions, just as in the radiometer, where the pressure is constant. Okay. So, if I'm keeping the pressure constant, so I'm looking for isobaric solutions. Because now P is a constant, when I plug it in, this part makes no effect when I start differentiating a constant, I get 0. So I'm looking for isobaric solutions. Okay, so I should have said, okay, that the exact solution to this one and this one was U equals 0, V equals 0, theta equals theta 1x, with the condition that P equals a constant. So that's the exact solution. So I found P equals a constant, and that's a solution, isobaric solution. Okay. Okay, so now, so we got V equals 0. So if V equals 0, then I can quickly take the, which color do you want? Yellow again? And every place I say V, I cross the term out. Now this one, I could cross it out, but let's remember again to multiply by H. This one, again, multiplied by H. This one and H. And those are epsilon. So let's see. So this one, this is H over L, which is epsilon. Epsilon hits that guy, we throw it away. So let's record the equation. So this one goes out, and let's record the equations. Because it's very simple. So we see conservation of mass for the channel problem just became this one, which was just V equals 0. Conservation of momentum okay, for this one, well, this was 0, this was small, by multiplying by epsilon, this is 0. The other one is T12 equals d dy of T12 equals 0. Another good thing about this problem is we started with something very hard, and at least the equations are extremely simple, which from point of view of PDE people is always good. The other conservation of momentum is, this is epsilon. The epsilon hits this term, so that one's small. This one was 0, so it's just d dy of T22 equals 0. The other conservation of momentum. And last but not least, here this is epsilon, V equals 0, so that one goes out. So this one goes out because V equals 0. This one goes out because it's epsilon. This one doesn't go out. It's a d dy of UT12. This one, so that one stays. This one goes out because V equals 0. This one goes out because it's epsilon. This one stays. So energy is, what was it? dV y of ut12 of so we have equations. And we're looking to solve the problem, as I said before, to imitate the radiometer isobaric flow. Okay. It's also observed experimentally that the pressure is constant in the channel. Okay, isobaric flow means P equals, say, 1, which means rho theta equals 1. Okay, now let's count the number of equations and the number of unknowns. Okay, so we have how many equations? Well, let's see. 1, 2, 3, 4. This one is trivial, but anyways. 1, 2, 3, 4 equations. How many unknowns? Well, we have U, V, rho, theta, but rho times theta is 1. So only 3 unknowns. And 4 equations. So we have to decide what equations. Okay, so which one do you think are the important ones? Okay, so the way Henning does it, Striftrup, wherever, okay, and I agree, okay, seems to me momentum is important. Okay, this one you can't avoid. Okay, so we'll solve these 3, get it, and those you can solve exactly. So what can you do? Solve those 3. Now this one, okay, what we'll do, or one way to think of it is, it tells us that the Q from Fourier wasn't exactly right. And this would tell us, oh, the correction of the Fourier law will be whatever makes this one work out. Has to be satisfied exactly. So this will give us the Fourier law correction. So Q will be the old Fourier from the heat equation, and then an additional term, and then an additional term will make this one balance. And the other way, you could just say, why not? If we can solve this one, we can write down the answer. Very simple expression. Let's compare our answer from doing elementary math with this computer experiment. If they look the same, not so stupid. If they look different, then it's stupid. Okay, so we'll find out. Only one way to find out is to do it. Anything else? Oh yeah, now we get into a philosophical issue, and I don't know the answer. Okay, so this is bothering, and I'm talking to Youngchung about this. So it's so this one was clear with the small, how to do this small parameter. You have H over L, okay. But what about this one? No small parameter. This length is as big as this length. Infinity over infinity. What is it? So then what Henning and Victoria Canada says is one way to argue. But it's only an engineering argument. I don't know if I don't like it, but that's, what can you do? So the engineering argument would be, or if you want to, it says, okay, we expect for this one that there'll be a boundary layer. Let's assume that there is a boundary layer, and we assume that there'll be a boundary layer of height h. So we look for a boundary layer solution of height h, which reduces this one to the same argument we used there. Okay, of course, for an engineer, makes sense. What you want to do is solve the problem, and any way you can solve the problem is okay. But for a mathematician, it seems to me circular reasoning. We assume the answer to find the answer, which is a little circular. So, as Henning says, Strothkorp says, any way he can use to find the right equations, he's happy. And I say, yeah, but it still bothers me that you have to know what was happening before you can, that there was a boundary layer to look for.